Hello guys, in this video we'll try to derive one more derivation, which is the second derivation from your model number 5 for the centrifugal pump. In that we'll derive an expression for the pressure rise in a pump impeller. So they might ask a question for you to derive an expression to calculate pressure rise in a pump impeller. So how will you do it? We'll just get to know the process of it. Number one, first you are going to assume a backward vane pump. Usually 90% of the cases we will use a backward vane pump. Okay, so backward vane pump. So for that, inlet and outlet velocity triangles are already drawn and kept ready here. Okay, so next, so since pumps are radial flow machines, no, so pumps are radial flow machines, so that is why we use Vm, which is meridional plane, velocity in meridional plane, as our reference in place of Vu. Now, okay, the total energy outlet of the any pump will be equal to total energy at outlet would be equal to total energy at inlet plus the work done by the impeller. Okay, so this you have to remember. So total energy at the outlet would be equal to the total energy at the inlet plus work done by the impeller. Hope you know the Bernoulli's theorem. So applying Bernoulli's theorem, from Bernoulli's theorem, what we have, that the total energy at the outlet is given by P2 divided by rho g plus V2 square by 2g plus Z2. So this is the total energy available at the outlet as per Bernoulli's theorem. That is equal to total energy at the inlet is P1 divided by rho g plus V1 square divided by 2g plus Z1. So this is the total energy which is available at the inlet. Now work done, it is given by U2 Vu2 divided by G. So this is the work done by the impeller, as we have discussed in the last derivation also. So now from this, the Z1 and Z2 you will be at the same level. So assuming what? The same height. Assuming same height. So Z1 would be equal to Z2 and V1 would be equal to Vm1. So what would be the above expression then? So P2 divided by rho g, I will bring the other one in the LHS, that would be minus P1 divided by rho g. Okay, that would be equal to Vm square. V2 is replaced by Vm because it is radial inlet. V1 equal to Vm there. So Vm1 square divided by 2g minus V2 square divided by 2g. Only V1 would be equal to Vm1 because it is radial inlet. You can observe here. V1 would be equal to Vm. Okay. So that's regarding that particular thing. Plus, of course, you have U2 into Vu2 divided by G. Okay. So from this, next, what can be done? So this is the pressure rise. So this is nothing but your pressure rise, isn't it? The pressure rise, that is equal to Vm square minus V2 square divided by 2g into, plus U2 Vu2 divided by G. I will take this as equation number 1. So pressure rise is nothing but again delta P. Okay. Is it fine? Next. Now, taking the exit velocity triangle, from exit velocity triangle, apply tan beta 2. So what is tan beta 2? Opposite. Opposite is Vm2 divided by adjacent is u2 minus of Vu2. Or you can extract the value of Vu2 from this, which should be equal to u2 minus of 1 by tan is cot. So Vm2 into cot beta 2. So I will take this as equation number 2. Now what I will do is also applying Pythagoras theorem, so what we have V2 square is equal to Vm square plus Vu2 square. So where you are applying Pythagoras theorem? In this particular triangle. If you zoom in here, V2 square is the hypotenuse, which will be equal to Vm square plus Vu2 square. Okay, so the Pythagoras theorem I have applied there. So once after applying Pythagoras theorem, next substitute the values. What value will you substitute here? Substitute the value of Vu2 from equation 2. So from equation 2, what we have, V2 square is equal to Vm2 square plus, this is the value of Vu2, isn't it? That is u2 minus of Vm2 cot beta 2 its whole square. Now a minus b whole square formula, a minus b whole square is equal to a square plus b square minus 2ab, isn't it? Applying the same thing now, u2 square is equal to Vm2 square plus, now a square u2 square plus b square Vm2 square cot square beta 2 minus 2a u2 Vm2 cot beta 2. Okay, so now what can be done next is taking Vm2 common. So we have Vm2 here as well as here. So taking Vm2 common, so what it will lead? It will lead to u2 square plus Vm2 square common. If I take common, it is 1 plus cot square of beta 2 minus 2u2 Vm2 cot beta 2, right? So now I guess you know what is the value of 1 plus cot square beta 2. It is cosec beta 2. Okay, so that is Vm square. I will be writing this as cosec square of beta 2 minus 2u2 Vm2 cot beta 2. Now what you are going to do is you are marking this particular equation as equation number 3. Now substituting the value of V2 in equation 1. Okay, what was equation 1? I will just pick that equation number 1. So this is the equation number 1 what I have. Okay, so in this particular equation I am substituting the value of V2. So what happens, we shall see. So Vm1 square would be as it is minus V2 is what? The whole thing, whatever you have. It is u2 square minus Vm2 square cosec square of beta 2 plus 2u2 Vm2 cot beta 2. So whole this you have for V2 divided by the value of 2g plus you have u2 Vu2 divided by g. Next, try to take 1 by 2g common, so 1 by 2g if I take common, so what will be left here? Vm square, Vm1 square minus u2 square minus Vm2 square cosec square of beta 2 plus u2, sorry, 2u2 because 2u2 Vm2 cot beta 2 plus 2u2 square minus 2u2 Vm2 cot beta 2. So this big expression you will get. So from this, what happens now? Anything would cancel. So I guess this would get cancelled here. So plus 2u2 Vm2 and minus u2 Vm2 cot beta 2. These both expressions will get cancelled. What else? You have one u2 square here and one more u2 square. You can combine these two. So final expression would be delta p is equal to 1 by 2g into Vm square as it is plus minus u2 square plus u2 square. So it is plus u2 square minus Vm2 square cosec Vm2 square cosec square of beta 2. So this is the final expression required for the pressure rise in a pump impeller.